Hi all, today we are dealing with the topic power quality in smart. Frequent occurrences of power quality events are the results of deficiencies in power delivery system. By incorporating and integrating smart grid technologies into the power delivery system can provide a clean power to the end user equipment with minimal disturbances. Both electric utilities and end users of electric power are becoming increasingly concerned about the quality of electric power. The term power quality has become one of the most prolific buzzwords in the power industry since the late 1980s. The reason for increased concern on power quality can be summarized into 5 points. First one, the new generation load equipment with microprocessor based controls and power electronic devices is more sensitive to power quality variations. The second point is that the increasing importance on overall power system efficiency has resulted in continuous growth of devices with high efficiency. The devices like adjustable speed motor drives and shunt capacitors for power factor corrections are being increasingly used to reduce the losses and to improve the efficiency. This growth is resulting in increased harmonic levels in power system. Also, nowadays the end users, that means the consumers, now have an increased awareness on power quality. They are challenging the utilities to improve the quality of power delivery. Coming to the fourth point, as we know, many things are now interconnected in a network and the failure of any component has much more important consequences. Also, with the penetration of DC sources, power quality issues increases considerably. Now, how can we define a power quality issue? Any power problem manifested in voltage, current or frequency deviations that results in failure or misoperation of customer equipment can be considered as a power quality issue. Now we will move on to various power quality issues. Power quality issues can be classified into 5 categories: transients, short duration voltage variations, long duration voltage variations, voltage unbalance, and waveform distortion. First we will look into transients. Transients are subcycle disturbances in the AC waveform and can be categorized as either impulsive or oscillatory. Transients are possibly the most damaging type of voltage disturbance. An impulsive transient is a sudden non-power frequency change in the steady state condition of voltage, current or both that is unidirectional in polarity. That means the polarity is either positive or negative. Impulsive transients are frequently referred as surges. The most common cause of impulsive transients is lightning strikes. Other causes include electrostatic discharge, poor grounding, switching of inductive loads, switching of power factor correction, capacitors, etc. Actually, an impulsive transient can damage a wide variety of equipments that is not rated for such high voltage levels. Even if the amplitude of the transient is not very high, the rise and fall rate of voltage can damage an equipment. Moreover, a repeated transients can damage. Now you can see a figure. In this figure, impulsive transient due to electrostatic discharge is shown. As you can see, it is unipolar in nature and the rise time of the waveform is in the range of less than 1 nanosecond. Now the second category of transients, oscillatory transients. An oscillatory transient is a sudden non-power frequency change in the steady state condition of voltage, current or both that includes both positive and negative polarity values. That means it is bipolar in nature. Now you can see the difference between impulsive and oscillatory transients. Impulsive transients are unipolar and oscillatory transients are bipolar. An oscillatory transient consists of a voltage or current whose instantaneous value changes polarity rapidly. Oscillatory transients again can be classified as high frequency transients, medium frequency and low frequency transients based on the frequency range and duration. Capacitive or inductive load switching is the most common cause of oscillatory transients. Switching on or off of the active power factor correction capacitors can also lead to oscillatory transients. Can also occur by abruptly turning off a motor load. In these situations, the system voltage will oscillate at a high frequency that decays within an electric cycle. The voltage overshoot occurs as a result of the oscillation and can affect equipment such as variable speed drives. In addition, the oscillation in the AC voltage can impact the voltage level of a drive's DC bus, potentially causing it to exceed its overvoltage trip point. Now you can see a figure. In this figure you can see oscillatory transients which is bipolar in nature. This has occurred due to switching in of capacitor banks. Now the question is how we are going to mitigate transients. The equipment can be protected from the transients by removing sources of potential ESD and using surge suppression devices. Good wiring practices can also help in reducing the effect of transients. High frequency filters can also be used to suppress oscillatory transients. Now we are discussing about the next category of power quality issues, which is named as short duration voltage variations. Short duration voltage variation includes sags, swells, interruptions. Each type of variations can be classified as instantaneous, momentary, or temporary depending on its duration. Short duration voltage variations are caused by fault conditions, the energization of large loads which require high starting currents, or loose connections in wiring. First we will look into interruptions. An interruption occurs when supply voltage or load current decreases to less than 0.1 per unit for a period of time not exceeding 1 minute. Interruptions can be the result of power system faults, equipment failures and control malfunctions. And these are measured by their duration. The duration of an interruption due to a fault on the utility system is determined by the operating time of protected devices. Instantaneous reclosing generally will limit the interruption caused by a non-permanent fault to less than 30 cycles. Some interruptions may be preceded by a voltage sag. Figure shows such a momentary interruption during which voltage on one phase sags to about 20% for about 3 cycles and then drops to 0 for about 1.8 seconds until the recloser closes back. Now the second category of short duration voltage variation known as sag. A sag is a decrease between 0.1 and 0.9 per unit in RMS voltage or current at the power frequency for durations from 0.5 cycle to 1 minute. The IAC definition for this phenomenon is dip. Voltage sags are usually due to system faults but can also be caused by energization of heavy loads or starting of large motors. Sag durations are subdivided into three categories: instantaneous, momentary, and temporary. You can see the figure. Figure shows a typical voltage sag that can be associated with single line to ground fault on another feeder from the same substation. In the figure, you can see a reduction in the voltage, which indicates sag. A swell is defined as an increase between 1.1 and 1.8 per unit in RMS voltage or current at the power frequency for durations from 0.5 cycle to 1 minute. Swell is exactly the opposite phenomenon as of sag. Swells are usually associated with system fault conditions, but they are not as common as voltage sags. One way that a swell can occur is from the temporary voltage rise on the unfaulted phase during a single line to ground fault. Swells are characterized by their magnitude and duration. The severity of a voltage cell during a fault condition is a function of fault location, system impedance, and grounding. You can see the figure. In this figure, voltage swell is caused by a single line to ground fault. You can see a rise in the voltage from 1 per unit, which indicates swell. The same kind of waveform can also occur by switching off a large load or energizing a large capacitor bank. The third category of power quality issue, long duration voltage variations. It includes overvoltage, undervoltage, and sustained interruptions. Voltage deviations at power frequencies for longer than 1 minute, that is meant by long duration voltage variations. First we will see overvoltage. An overvoltage is an increase in the RMS AC voltage greater than 110% at the power frequency for a duration longer than 1 minute. Overvoltages are usually the result of load switching, for example, switching off a large load or energizing a capacitor bank. This condition occurs because either the system is too weak for the desired voltage regulation or the voltage control methods are inadequate. For example, incorrect tap settings on transformers can also result in system overvoltages. An undervoltage is a decrease in the RMS AC voltage to less than 90% at the power frequency for a duration longer than 1 minute. Undervoltages are due to the switching events that are opposite to that of the events that cause overvoltages. A load switching on or a capacitor bank switching off can cause an undervoltage. While discussing causes of overvoltage, we have already seen switching off a load or energizing a capacitor bank causes overvoltage. Here it is exactly opposite. A load switching on or a capacitor bank switching off causes undervoltage. The term brownout is often used to describe sustained periods of undervoltage. Now we will see sustained interruptions. When the supply voltage has been 0 for a period of time in excess of 1 minute, the long duration voltage variation is considered as sustained interruptions. Voltage interruptions longer than 1 minute are often permanent and require human intervention to repair the system for restoration. If the time duration is less than 1 minute, it is considered as interruptions and it will come under short duration voltage variations. When it exceeds 1 minute, it is considered as sustained interruptions and it will come under the category of long duration voltage variations. Now, voltage unbalance. Voltage unbalance, also called voltage imbalance, is sometimes defined as the maximum deviation from the average of three-phase voltages or currents divided by the average of three-phase voltages or currents expressed in percent. Also, the ratio of either the negative or zero sequence component to the positive sequence component can be used to specify the percent unbalance. The primary source of voltage unbalance of less than 2% is single-phase loads on a three-phase circuit. It can also be the result of blown fuses in one phase of a three-phase capacitor bank. Severe voltage unbalance can result from single-phasing conditions. You can see the figure. First you can see a balanced system, VA equal to VB equal to VC. Second case you can see unbalanced phase system. The three phases are not equal, they are different in magnitude, and you can see a waveform. The three phases are having different magnitude. So that indicates there is an unbalance. Now the last category of power quality issue, waveform distortion. It includes DC offset, harmonics, interharmonics, notching and noise. Waveform distortion is defined as a steady state deviation from an ideal sine wave of power frequency. Now we will see the first one, DC offset. The presence of a DC voltage or current in an AC power system is termed as DC offset. This can occur as a result of a geomagnetic disturbance or asymmetry of electronic power converters. Direct current in AC networks can have a detrimental effect by biasing transformer cores so they saturate in normal operation. This causes additional heating and loss of transformer life. DC current may also cause the electrolytic erosion of grounding electrodes and other connectors. Now you can see the figure. In this figure, the green color waveform has a DC offset of 3 volt. Now we will discuss about harmonics. Harmonics are a form of voltage or current waveform distortion. A harmonic refers to a component of a waveform of a frequency that is multiple of the fundamental, generally 50 or 60 Hz. In India, our power frequency is 50 Hz. So, the third harmonic for distribution systems in India would be 3 into 50 Hz, which is equal to 150 Hz. Harmonics are a relatively steady state condition, not momentary in nature. Now we will discuss about the causes of harmonics. Harmonics are caused by nonlinear loads in the electrical system. Nonlinear loads draw non-sinusoidal current from a sinusoidal voltage source. Examples of nonlinear loads are AC or DC motor drives, electric arc furnaces, inverters, var compensators, SMPS, etc. Industrial customers are increasingly using drives for more precise motor control and to improve energy efficiency. Consequently, the potential for greater harmonic distortion rises. Now we will see what are the effects of harmonics. High levels of harmonic distortion can result in increased transformer, capacitor, motor or generator heating. Electronic equipment that relies on voltage zero crossing detection or sensitive to voltage wave shape can malfunction. Other potential effects include incorrect readings on meters, misoperation of protective relays and interference. Devices in parallel with harmonic sources will see a distorted voltage waveform and consequently these electronic devices can trip, potentially causing plant shutdown. Also, harmonic currents produces additional efficiency losses and consequently system components such as cables, circuit breakers and transformers may have to be oversized. What are the effects of triplet harmonics? Triplet harmonics are defined as odd harmonics that are multiple of 3. That is 3, 9, 15, 21, etc. In a three-phase star system, triplet harmonics come together in the neutral conductor, creating a large neutral current. can see the figure. This can result in efficiency losses and requires an oversized neutral conductor. Now we will see resonance. When the harmonic frequency coincides with a power system natural frequency, resonance occurs. This condition sometimes occurs when combining drives with power factor correction capacitors. Resonance results in the amplification of the harmonic current and can lead to blown fuse or transformer overheating. After all, the negative impact of harmonics may not be immediately evident, but over time can result in increased power demand, system loss, and shorter equipment lifetimes. Now the most important question, how do we mitigate harmonic distortion? We can go for harmonic filters, passive or active, can be added to the system to suppress harmonic frequencies. Passive filters are tuned to filter a specific frequency or group of frequencies. Active filters measure the harmonic currents present in the system and generate opposite harmonics to cancel those produced by the harmonic sources. If the problem arising are a result of harmonic resonance, it could be worthwhile adding or subtracting a small level of power factor correction capacitance to shift the overall system natural frequency. Also, to reduce the harmonic distortion due to variable frequency drive, use a rectifier with a higher pulse than 6. As we go for higher pulse, harmonic content naturally reduces. Another method is to place a AC line reactor in series with the incoming AC power line, which along with the DC link chokes help to smooth out the flow of current to the drive. Reduced harmonic distortion can also be achieved by using a pulse width modulator rectifier that uses switching devices instead of diodes. Now you can see the figure. You can see harmonic waveforms. Third harmonic waveform you can see in red color. Bass sine waveform when added together with third harmonic we will get distorted waveform.